Thanks, John, and thanks all of you. I'm really happy to be here today. So I think I'm the only homogeneous catalysis person in the room. And today what I'm going to be talking about is work that other people have done. As in my other role as Chief Science and Technology Officer, I'm in charge of strategy and investing in autonomy and AI is something that I'm really passionate about. PNNL is really passionate about when moving that forward. And so I'm excited to share some of the tools that we've developed and really represent their work. And so one of the things at PNNL is that we have a long history of physics-informed machine learning and using that really strong foundation to ensure that our models are things that can be validated and that we can have confidence in. And so even with neural networks in physical sciences, those don't produce highly reproducible results without physics-informed behind that. And also being able to use computer architectures is another important thing and a skill that we bring to this. And so being able to take that physics-informed foundation and then the strong partnership between domain scientists and data scientists, which is absolutely critical for success here, that's started to allow us to build tools as we incorporate large language models that we can have confidence in. And so I'll talk about the tools that I show here as I go through my slides. And so first I'll talk about just physics-informed machine learning. And in this case, it's continual learning. So what we observe is that if you have a model and then you add new data to that, unless you retrain the entire model, you start to have what's called catastrophic forgetting. And so by using continual learning, we're able to avoid that catastrophic forgetting. So in this case, it's a sample of 1,000 experimental data points. And as they added new training, if they used typical machine learning, they saw the forgetting. But if they used physics-guided continual learning, in this case, redox flow batteries, they were able to see that that was largely maintained, even out to 5 different new pieces of information added. This is an example that we didn't build this tool. We partnered with Microsoft and the Azure Quantum Elements tool. And in this case, it was materials discovery, again, batteries. And I've given a couple of battery examples, but I figured the step from batteries to electrochemistry and electrocatalysis is a very big step. And so in this case, they started with over 32 million structures. They then used a series of from simpler to more complex, either machine learning or high performance computing to down select, in all cases using some level of physics guided simulation. Down selected that to about 150, and then they brought a human fully into the loop to look at those 150 and say, okay, these ones already exist, these ones aren't going to be stable, these ones are too expensive. Narrowed that down to 18 materials, and then PNNL was now involved, human in the loop, making these in the lab. We made 4 different materials and ultimately came up with one material that was a new composition that hadn't been seen before. Now, in this case, this battery is not impressive, right? A potato battery is probably better. But the point here was accelerated discovery. And one thing I'd like to point out is down to the 150, that took about 2 weeks. Once we got in the lab, that took about 3 months. So there's still a need to, some of the tools we're seeing here, there's a need to accelerate what we're doing in the lab as well. And that will continue to be a slow step. So Cactus is a tool that is built on the large language model framework. And it's an agentic framework to be able to call different tools up with this tool to answer questions and query what we already know. So in this case, if you wanted to know the molecular weight of something, you could query that quickly. I remember as a graduate student learning that there was this website that had NMR spectra on it. And if I knew where that website was, I could go, oh, let's go look at that NMR spectra. But if you didn't know where that website was, you were kind of out of luck. And so this connects you with all those things without you knowing that they exist. So molecular weights, structures, partition coefficients, different factual information that's already there to reduce the effort to do experimental research and to query the literature. This next tool, Chemist, is really fantastic, and it's actually related to what Sulio was just showing. So what they've done here, again, it's using large language models, but augmenting them by taking a series of papers and looking at all those papers. But what is really exciting about this tool to me is that it takes text graphs, images, and it vectorizes all of those so that it can look at all of those on an equivalent plane. And then it create this with this knowledge model, it creates a series of knowledge graph or nodes. So when you query it, you can tell how it came to the conclusion that it came to. And it also allows you to compare different papers. So in this case, we were using a database of 370 papers. So it not only allows you to discover information already in the literature, allows you to see how that's compared and verify that the information it's coming up with makes sense for what you were looking for and isn't a hallucination. In this case, one thing I did want to point out was the model itself does create these different points in the knowledge model or the knowledge graph, but an expert can then go refine those. So for instance, one might be catalyst synthesis, one might be characterization, but then you have an expert coming in and verifying that that's the right thing to look at. And this model chemist is one of the agents that's being used in a new program through the Accelerate DOE program, where they're trying to understand catalyst degradation. And in this case, they take the observables, and then they have two time frames that they're looking at, both a short time scale and a long time scale, and trying to understand what that degradation rate looks like, and be able to predict that ahead of time, ultimately, of course, to be able to avoid catalyst degradation. This last example and tool I'm going to present is one I'm particularly excited about. It's called ChemReasoner, and the idea behind this tool is to actually discover new catalysts. So it goes beyond just discovering what's already in the literature and extrapolates that to potentially new catalysts. So it's able to hypothesize, to generate hypotheses. And this just uses large language models without a expert augmentation, but it uses DFT calculations to augment. So as it's hypothesizing and learning, it's using DFT to confirm those calculations. It's able to also generate the heuristics rather than having those defined ahead of time. But again, you can go back and follow the logic path that it used so that you're able to, as an expert, follow and understand and verify that what it's doing makes sense. And the last comment I wanted to make was just that energy efficiency is going to be absolutely critical as we go forward. I think all of us are aware of how much power the data centers are using. And so being able to not just bring our models to bear on the right problems and be energy efficient, but also our compute infrastructure and making sure that that is energy efficient as well. And my last slide is just to acknowledge the people that are spanning this space. So these are some of the people that are doing the work that I've just represented. Domain science and data science is not an obvious connection point, and having the ability to communicate across those, all of you and all of these folks, I think is incredible. And it really does take intentionality, because that conversation can be really hard and take some time to happen. So I congratulate all of you to be willing to do that, and thank all of these folks here for being able to do that and willing to do that.